talking about F1 teams. That's Formula 1 teams, right? Maybe after the class or during the class. In a matter. What's that?
There have been times I've watched F1 during your class. It's not your class.
Okay, that's good to know. I mean, you probably can't really watch anything during my classes because there weren't that many of you guys, so I would have noticed. Are you recording? Yes. Okay, so what was the last thing we talked about? It was the example on. We just went over it, all right?
Yeah, you gave us the diagram.
Yeah. And that's all we're gonna do for the reheat and regeneration, and what's that?
Moving on to gas cycle.
Yes, we are moving on to gas cycles. We will do a small introduction to gas cycles, and then we'll come back to it later in this semester. Right? We will have one whole chapter. Your biggest chapter actually is going to be on jets, which makes a lot of sense. It's the propulsion class. Yes.
Regarding our first homework next Wednesday.
Next Wednesday. Yes.
If we wanted to, if we had like decent notes from our previous thermo class, like would that be sufficient to do the homework, or like we gone any further than what we covered?
I don't really know what they covered in your thermal class, so I can't really answer that question. But did they go over ranking cycles? Then yes, I guess you should be able to. You had your thermal with Reynolds, right? Tony, right? Yeah, I think we should ask him to teach all thermals. But yeah, so if you have had gone over cycles in your thermal class, you should be able to answer all of the questions on the homework. Well, I've seen some people go over the Brighton cycles and gas cycles as well, so you should be fine. Any questions? Okay. So the first part of today's lecture is going to be, I guess, most of today's lecture. We may actually need to leave the class early because of some things I need to do. So most of the class today is probably going. Oh, okay.
I might skip my class after this.
That's tempting.
Okay. So let's go over this quick. We are going to have an introduction to the gas cycles because we didn't really do an introduction to Rankine cycle because Rankine cycle, as I've said many times, was not the focus of our class, right? But we should do an introduction of the gas cycle, and this lecture is also already posted. So when we talk about gas cycles, we are usually dealing with a lot of history here, but the idea here mainly started with the thing that we are going to focus on is mostly the Otto cycles, the diesel cycles, and also the jet cycles, right? Specifically the jet cycle, this is the thing that we are going to focus on. One thing that is similar to all of these cycles is the presence of a combustion, right? So you have a fuel-air mixture. You mix your working fluid. Your working fluid is always, not always, but mostly air, right? You mix it with a fuel, and then you send it to a chamber, combustion chamber, right? Compress the fuel, or sometimes you don't really compress it, depending on the type of the engine you're using. If there's combustion, then you are, in the case of jet engine, you are going to produce some thrust, right, because of that combustion. Does it make sense? I mean, it's a concept that you've seen. I'm pretty sure you're familiar with the internal combustion engines, maybe even more than a lot of the faculty here, not just me, and especially if you follow the Formula 1 competitions. I guess you have to be familiar. As I said, Industrial Revolution was the time when we started to transition manufacturing processes, transition between like doing the dirty work by hand to doing all the dirty work and all the movements by machines. So, 3 main cycles. Any questions so far? Just a little bit of history. We have 3 main cycles when it comes to internal combustion engines in general. in the combustion unit or the gas cycles, we have the Otto cycle, which are mostly related to spark ignition engines. We have the diesel cycles, which are compression ignition engines. Both of these have ignition happening inside them, but the compression in the diesel cycles is a little more intense, if you will. And then we have the Brighton cycle, which is going to be the topic of discussion for like 75% of this class. And that is an example of those is the gas turbine cycles. There are other examples that we are not going to cover. For this class, we are mainly going to focus on these three. Okay. How does a spark ignition engine work? First of all, you can see a GIF or GIF on the process of this process, depending on how you pronounce this word. You can see animation of the spark ignition process here in the picture. You have a piston moving, and you also have the inlet and exhaust. I'm assuming this is a familiar concept to you. You have seen this before. The idea here in the spark ignition engine is that we are going to feed the fuel and air simultaneously into the cylinder, right? And then when we are compressed enough, we are going to have the ignition, and the ignition is going to cause a release of energy, of course, which is going to push the piston downward, right? And then you are going to release the exhaust gas, and so on and so forth. So this is the principle, the biggest principle, the most basic Otto cycle that you can see. There are different parts to it. The intake of fuel or air, which is called the induction, the compression of fuel or air, then ignition, and also the exhaust out. The compression ignition engines, or diesel cycles, you are going to only feed air into the cylinder. Okay, so that will be the main difference here. So the first process, they are not going to be fed to the cylinder together. Air is going to be fed to the cylinder by itself. Then you have the compression, and then you inject the fuel into compressed air. Right? So that's the difference. That's the biggest difference between these two. Everything else is going to be exactly the same. You have the intake of the air as the diesel. In the diesel cycle, we have the compression of air, and you have the ignition, which is a process that includes fuel injection, rapid mixing, and also the auto ignition, and we also have the exhaust out. Any question about this cycle?
Is it based on the way the fuel is ignited? Like the diesel engine produces more torque than the gas engine. Is it based on the way it ignites, or is it something to do with the diesel?
That's a very good. That's what I wanted to discuss with you guys, and I wanted to ask your opinion on this. What do you think will cause more torque in the diesel engine? So, the Otto cycle engines, I don't want to call them regular internal combustion, I want to call them the Otto cycle engines, which are mostly installed on cars, are going to be a little faster, right? But the diesel engine cars, like trucks, like big trailers, are more powerful, so they can haul more weight, right? But they are not going to be as fast. The acceleration is going to be that's the common knowledge, right? Why do you think that is? Think about it. Does it have anything to do with this cycle? Lower RPMs. Which ones? Why do they have lower RPMs? Think about it. It's just a brainstorming. Heavier cylinders. I guess that's it. Yes.
The gas that we're using can heat at lower temperatures, and on diesel engine it takes higher temperatures to max. That's why I have low RPM.
Okay. Yes, yes, definitely. Yeah. It really depends on it, but okay. Well,
Is it information like how long it takes for like the same volume of gas to ignite?
how long does it take? It is mostly the lower RPM actually goes back to the compression, but you were on the right track for the torque thing. So we need to compress since this actually it's all true. Since we need to compress this a little more, we need higher pressures for it to ignite, right? So we have a more compressed air, right? What will happen when you have a more compressed air? When you ignite it, it is going to release more energy, right? So it can haul more. You wanted to say something too, right?
Yeah, that was pretty much it.
Okay. So that's basically the idea that's happening here. And you already knew the answer. There are other things that will go into effect here, but I guess one contributing factor is the thing that you all mentioned. Any questions? Okay, so let's actually forget about this part. This is a very combustion related part. Let's talk about the gas turbine engines. So gas turbine engine, as I said, is going to be the focus of our not this chapter, but essentially the course itself. The gas turbine engines are usually open systems. What does it mean? I mean, it's true for most of the combustion cycles, but this essentially means that we have an intake in an air inlet, an intake in the air inlet, in the air inlet here, and then we have an exhaust. And during this process, we are going to have a compressor, which is going to be in charge of the compression of the gas and of the air, right? The compressed air then is sent to the combustion chamber, and then we will have the exhaust nozzles in which we exhaust the air-fuel mixture, okay? And then this whole process is going to generate thrust, right? Is there any questions about this? No, that's good. So as you can see, it is actually very similar to the previous examples, these two. So we have the compression here, and then the combustion chamber, the exhaust. Compression, combustion, exhaust, right? Same is true for the Otto cycle. The only difference is that, I mean, it looks a little different. That's the idea. And it doesn't have any moving piston that is going to. Let me ask you this. That's actually a very good I guess, segment to this. Why do these three cycles, the first two diesel and Otto cycle, look different compared to the Brayton cycle, the gas turbines? What is the most important? Yes.
Because in this one, you're using the exhaust, really using the exhaust, and like, automotive engines, you're using the drive shaft, so you're not heavily using the exhaust.
We are not using the exhaust here as well. It's that we are going to use the exhaust velocity in the calculations, but that doesn't mean we are using the exhaust.
Like the thrust is like, you're using the thrust directly from the combustion.
Okay, you're getting a little warmer there. You guys can jump in. You don't have to. The direction of. Can you elaborate a little more?
Kind of like what you're saying, like how with the combustion engine is transferred to a shaft, kind of like I guess perpendicular to it, and with the gas turbine it's usually inland.
That's basically I mean, as I said, is there anyone else?
Also, the purpose is different for a gas turbine because you're using solely like exhaust power for like thrust mainly, while in like car engines like the last few cycles, you were using it to like reroute mechanical power to other things.
So the idea here, yeah, exactly. So, I mean, you're not using the exhaust power, but the idea is you have the moving part, and you have the turbine, which is this part, right? And the combustion moves the turbine directly, right? But then in an internal combustion engine, what happens is that your exhaust pushes a piston down, right? So it is a linear movement, right? But you don't want to have a linear movement in a car, right? You want to have rotating movement. You want your car tires to rotate, right? So you have to have a mechanism. That's why you have the flywheel, all of those things that you have in an internal combustion engine that is going to change change the type of the, have you guys has what's it called? That's the course that is taught by Dr. Rashidov. Kinematics, yes, kinematics. Have you passed kinematics? You have seen a lot of concepts like changing the linear movement to rotating movement. So that's the idea of the internal combustion engine. But in the gas turbines, we don't really have that. So you may ask, we don't really change that movement. So we actually have a rotating turbine. The shaft is already rotating, right? So if you put two tires in front of that shaft, the tires should start rotating, right? So you may ask yourself, why don't you have a gas turbine on a car? Because we don't really need to. Less efficient. Why would you say that? Is there any other reason that you can think of? Dangerous. That's a very good, yeah.
With an aircraft, you know, we speak about like immediate power acceleration, more concerned about cruise speed, stability, and stuff like that. The car, we talk about 0 to 60 time, normally cares about 0 to 60 for aircraft engines. So you need that immediate mechanical performance for the car.
Yeah, and so all of you are actually on the correct path, and it is not in general, it is not a very practical use of a gas turbine. In order to be able to generate that much thrust, the thrust you need really to do this, to move the car, first of all, you have to have that power transfer mechanism. It doesn't transfer from a linear movement to rotating movement, but its direction has to change, right? It's rotating this way, and then you have to change the direction to this. So you have to have a gearbox there, right? Yes, no, you have that.
What cars using superchargers? Don't they use gas center because they use the supercharger to compress the air and put it back in the engine?
I mean, all of these cycles are gas-based, right? The difference is just the mechanism you are using, like the type of, I guess, motion you are producing, right? That's the only difference. Don't make it complicated. That's why don't we have gas turbines as a car? That's the question, right? Not different types of engines on cars, right? So one thing is that we need to change that. We need to have something that is going to help us change the direction of rotation, right, on a gas turbine. And in order to produce that much power, we need to have a big gas turbine compared to a small internal combustion engine, right? That's actually, I mean, when they were working on this, we didn't really originally have the gas turbines, mainly because of this, because it would have been very impractical to put something like this on a car, on a moving car, right? Think about it, like gas turbine, okay, it's going to be very impractical. So the size constraint and also the efficiency, all of the points you mentioned are actually pretty on point. So let's move on. What are the different types of gas turbines? We have actually, let me go ahead a little bit. Yeah, we have 4 main types of jet engines that are going to use the Brayton cycles. The first one is the high bypass turbofans. This high bypass, and we are going to talk about them a little more later, but these high bypass turbofans are actually have 2 sections. The first one is the bypass. When the air doesn't go into the engine, the jet engine itself, just bypasses the engine, hence the name bypass, right? So it goes around the engine. And then some of the air goes into the engine. The bypass ratio is going to be very important here. How much of the air is going to bypass the engine and go to the exhaust directly. And these type of jet engines are mostly used in lower speeds. Then you have the regular turbofans or turbojets. all of the air goes into the engine, then you have the combustion process, all of these things, right? You have the exhaust thrust generation that we are going to talk about. These are also low Mach number aircraft, but they can do supersonic, right? Lower Mach number compared to ramjets. Ramjets and scramjets are going to be the type of jet engines that we are going to use in supersonic or sometimes, like for scramjet, hypersonic situations. So I have two questions for you here. One of them is directly related to propulsion. The other one is related to aerodynamics. I don't know if you have covered this in your aerodynamic course, but it's not I think we have talked about it in orbital mechanics, though. So you should be, those of you who have been in my orbital class, you should be able to answer this question. I'm pretty sure everyone knows this though. What is the difference? It's a very simple question. I should have made it this way. So what is the difference between the hypersonic and supersonic regimes? One. 25. No. There's a 5 somewhere.
I thought it extends up to 25,
There's
there's a 5 in it somewhere.
a 5 in it somewhere, okay.
I don't know, man.
How about 0.5? No.
Not 0.5. No,
Not 0.5.
that's not high.
Any other ideas? And please jump. Think about it. 5. 3. Let's actually go around the room and see what everyone thinks. You said 3, then Igor, and then we go around. And if you don't want to answer, that's all right. Just say I don't want to answer. 3.5. Above 2. 5.1. And you already said 5, right? What about you? And no idea.
I'm going to retract it to
5. 3. 10. 4. I'll go. So those of you who said 5 are very close, are true, are correct when it comes to the convention that is set for a hypersonic flow. But in reality, hypersonic flow doesn't have a set point, right? Hypersonic region doesn't have a set, and it really depends on the type of the wing, type of the machine, type of the engine you have, right? The criteria of hypersonic flow regime, is when you will have aerodynamic heating, right? So it mostly for shuttles happens around 5, right? When you are on Mach 5, you will have aerodynamic heating. That's why we don't really use metal in a shuttle, right? We use ceramic, right? And the body outer, because they can tolerate a lot of heat, and shuttles can go up to Mach 20, right? Definitely higher than Mach 5. So they will definitely experience a lot of aerodynamic heating. So keep that in mind. Most people use 5 as their range, but it is not a correct way of representing hypersonic regime. Hypersonic regime is related to the heat transfer that is happening there, right? So if you end up working for a government agency working on hypersonic devices, keep that in mind. Mach 5 is not the criteria. Aerodynamic heating is, right? So you have to be able to do some shock analysis. Yeah, you have to do a lot of analysis. That's for sure. Okay, and the second question that we wanted to talk about, is the difference between ramjet and scramjet and the regular jet engines. Does anyone know this? Well, I'm pretty sure you have heard the name ramjet and scramjet, and they I guess sound cool. Yeah. Exactly. So, Drew, right? So as Drew said, the ramjet and scramjet are essentially based on the idea that at a very high speed, you don't really need to compress the air. As long as you design your nozzle, your inlet, in a proper way, you can actually achieve the compression ratio you need for combustion. That's why you don't really see the compressor stage in either the ramjet or the scramjet, right? But what is the difference between the two, between the ramjet and a scramjet? Pressure within the engine.
At least on the diagram, it looks like there's some kind of pressure buffer at the front or intake of the ramjet, and the scramjet seems more like a constant gradient.
Can you relate it to velocity?
Well, you use Bernoulli's
You're in supersonic situation. Definitely compressible. Bernoulli's doesn't apply here. That's for sure.
It seems like the ramjet kind of has to have some contours in it to actually create the ram effect, like compressing it, and then the scramjet going so fast that you don't really need that state. It's just compressed. Once you shrink the diameter, you have to go around that.
Okay. I mean, I can't say I can't really say you guys are giving me the wrong answer, but the main difference, or I can say that's actually, but that's all right. But the main difference between a scramjet and a ramjet is the fact that the scramjet, when you compress the air, you bring down the Mach number to a Mach less than 1. So you are going to be in the subsonic region. But in a scramjet, you don't really need to bring the speed of the air down to a subsonic speed. And because of the design, because of the shape of it, you can actually generate the thrust you need, right, for that velocity. So that's the main difference. You are going to have, in a scramjet, you're going to have supersonic all the way, right? Inside is going to be supersonic, outside is going to be supersonic as well. And inlet exhaust, the velocity is going to be different, but you will always stay above the supersonic velocities, yes. That's a very good question. That was the next thing that I wanted to discuss. So what do you think? Yes.
I feel like the two most common ways to stay like either an extra turbojet, so a turbofan on it, so it's like a two-stage kind of process where they're brought from the jet that has a turbofan and turbojet.
So exactly. So these ramjet and scramjet cannot start from zero air velocity, zero airspeed. Right? You have to be at a very high speed before being able to use these ramjet and scramjet, right? So you have to make sure that you are already in air, you are already airborne, you are already moving at a supersonic speed to be able to start the ramjet, right? To be able to have the ram effect, right? They can't really, because they don't really suck air in, right? There is no way they can start that move. There's no compression. There's no compressor, right? So you have to have some air coming in by default, right? Okay, is there any other questions? Yes.
Is there a point in which the scramjet, once it passes 8 or 15, Mach 15 or something, is it's moving so fast that combustion isn't possible anymore?
Huh. That's a very good question.
We find out.
I honestly, we have had this discussion, to be honest with you guys, in a group meeting of us, but it wasn't the main topic, so we didn't really go into it. And I don't really know the answer, so I can't give you a correct answer on this. I have to go and do my own research. But let's do this. This was a very good question. Where is Nicholas? He was supposed to give a presentation today. I just remembered this.
I have no clue.
Okay. Okay. Yeah. What's that? Negative bonus. Yeah, that's for sure. Yeah. Let's do this. Let's do a 2-page paper on this as a bonus. And whoever can give me a correct answer, what will happen to scramjet when your velocity goes past the combustion limits? Okay? What do you think about it? I think that's yes.
Can I share an opinion about this?
Sure, yeah. Sure.
Usually on when they use scramjets, they use run access, experiments. They're dropping down from airplane that's already in the air, and they're starting from when it's supersonic. But we're going to fly with a rocket, it's going to reach up to 20 times the speed of sound, but they're starting from the ground and they're going up. They're using the Propulsion engine. But when we use Scramjets, we're using them on the experiments, and we can only reach outside. How much they reach? Like 7, 8 times the speed of sound. That's why I don't think that's something possible.
Yeah, that's a good point. So that's actually your opinion. I love this discussion because I can always ask more questions. So your opinion is actually correct, right? The scramjets usually don't go higher like Mach 10, Mach 11, right, whatever. And we use rockets for those. So what's the difference between a rocket and a scramjet or any jet engine? What's the main difference? Yeah, I mean you have to talk about one by one. Yes, yes. It carries its own oxidizer. So essentially you don't have an inlet on a rocket, right? It doesn't really matter what is the speed of your moving at, right? Because it doesn't really talk with the inlet air, right? So rockets can go very high, that's true. But that really doesn't answer what was your name again? Zach. That really doesn't answer Zach's question. What if we go beyond the limit, right? And that's what I want you to find an answer for. Yes? That's what I would guess, right? But I'm pretty sure there are some. Yeah, let's say the thing is okay. So do we know about shock wave? We will talk about shock waves later if you don't. But do we know? Is there anyone who in this class who knows about shock waves? You are having flashbacks. We have talked about this. Little bit in orbital mechanics. Okay.
Those equations where it was like propulsion and propulsion drag, like this is your Mach, weight drag.
Yeah. Just remember that. Okay, so we will go over the shock waves, but let's keep it as a bonus point at this. Like let's not have any further discussion on this. Let's see if we can find a good solution. And if you submit this paper, I will drop one of your homework. Okay, so let's instead of. So the question is this. The question is what will happen to the scramjet if the velocity of air becomes higher than the combustion time scale. So your fuel inside the fuel air doesn't have time to combust. Right? What will happen? Is this something that's possible, or what will happen? Okay, so if you can find a solution, it doesn't really matter if you find the solution, the answer to this question, as long as you go there, you like read a couple of papers, journal articles on this, or you read, I don't know, websites, whatever. You read something that is related to this, and you can come up with a coherent answer, right? You will get it. Yes.
Well, if you want to have time to combust, there's not going to be propulsion forward essentially. So what essentially just be limited velocity to whatever that kind of max speed is.
That's the idea, right? But what if you have to go beyond that limit, right? And the thing is, it shouldn't really get to that limit because of the shock waves, right? That shock waves inside both of these ramjet and scramjet work based on the shock wave principle, right? So you have shock waves. Shock waves are very compressed pressure waves, right? Before the shock wave, you have supersonic velocity. After it, you either have supersonic or subsonic velocity, right? And you usually have a huge drop in the velocity of air. So this really shouldn't happen, right? And if it happens, as you said, that we can't really use this scramjet. That's what I'm saying. You shouldn't really find if you couldn't find an answer, as long as you can explain the phenomena, why this question doesn't make any sense or whatever, right? As long as your answer is coherent enough and you have some references, right? Yeah, but I really like this discussion. That's a very, these are the things that you are going to remember. None of the equations will stay with you. And I also wanted to mention this, that we had the X-51 that was tested in I think they started testing X-51 aircraft in 2010. It's an experimental aircraft that uses a Scramjet. It actually reached 4,828 kilometers per hour during a 3-minute flight under the Scramjet tower. And distance from the US to the other side of the Earth is 10,000 kilometers. So it could go around the Earth to the other side in like 2 hours, right? Which is, as someone who has to go around the Earth to see his family, I know that I would definitely sit in that airplane to get there as soon as possible. No, the laws are going to be different at different altitudes. That's for sure.
It still has an effect on the ground.
What's that?
Even if you're so high in altitude, it's still going to have some sort of effect on the ground.
Yeah. You are going to generate a lot of sound waves, right? But your altitude is going to be different. Let's say you are in above atmosphere altitude, right? How much impact do you think that is going to have on the ground? Very little. Right? The gravitational effects are there, so you are going to go around there, but you are not really affecting the atmosphere that much, right? And okay, I guess we talked about this. That's the only thing that we will talk about the impulse. Do we know what impulse is? Have you heard about this parameter? But how do we calculate it though? That was it. That's all right. Natural log. We'll get that, don't worry about it. So, but because of a very higher, the significant increase in a specific impulse, Scramjet and Scramjets are going to have a longer range and ability to carry larger payloads. And actually, this is yeah. This is the first flight of X-51.
People awake.
May 2000.
Okay, can you see it?
I can. More left, more left.
Okay,
Okay, I got him now. We're fine.
good trajectory. She's climbing straight. On switch is safe. We have a booster burnout. Towards 5-2, we show Carson, please.
Okay, let me ask you one question. Yeah. Would you say
Good release.
this
People awake.
is not higher than Mach 5, right?
Good
Would you say this is hypersonic or supersonic?
Okay, can you see it?
I can.
You have
More
to
left, more
elaborate,
left.
right? Why would you say this supersonic? Why would you say this hypersonic? Actually, stop here. What do you expect to see during the hypersonic flow? Think about a shuttle re-entering the atmosphere. What do you see there? Aerodynamic heating, a glow, as you said. It's essentially, you have a shock wave, a blunt shock in front of the shuttle. You have ionization, you have plasma present there, and a lot of heating, a lot of aerodynamic heating. And that's what is going to cause the glow, right? But I think that's a very good starting point for shock wave analysis. But So essentially, based on what I'm saying, is that we should see something like that on this object as well, right? If we want to determine that we are in a hypersonic region. But that is not necessarily the case, right? Because the shape of the object is going to be a very important determining factor in the shape of the shock wave, right? The shocks here, for all we know, can be very close to the body. That's why we don't see that glow that you mentioned, right? That may be the case, right? I don't know. I don't know if it's a hypersonic or supersonic. I'm just saying that we should see the shock waves. We definitely do see the shock waves because shock waves can be visible. But because of the slender type of the shape of this body, that shock wave can be actually very close to the body, which means that higher aerodynamic heating because you have a very compressed air around the body, right? But we can't really say if we don't do the analysis, if that makes sense. Yes?
I remember reading some report about the hypersonic missiles specifically, where they talked about how like they'll become the next like nuclear deterrent. You can launch one, and it's fast enough that like whoever you launch it at had like 20 minutes to respond, and then you change one, it's like turn it around. So it's I already launched the missile, you have time to decide, but like they get there so fast and they move so quick.
Yeah.
Yeah.
Yeah, that turning around part is not related to propulsion or aerodynamic. It's more related to control. You definitely need to have propulsive forces there, but yeah, these are hypersonic vehicles are a very hot topic, especially when it comes to China and United States.
Where's the intake right there? I'm assuming that's flying right there. That's like a rendering of it. Where's the intake?
Where do you think the intake is? At the bottom, yeah, exactly. That's underneath it, yeah. Okay.
Mine's not going to stay put, but when it releases going up, the angle was increasing.
What's that?
When they drop it's probably out of time, but when they drop the missile, the experiment just goes up for a while and then goes cruising out.
Why do you think that is?
Yeah, isn't
Good release. Stay fluid. Good booster.
It is actually going down.
Okay, can you see it?
I can. More left, more left.
Okay.
Okay, I got him now.
And
We're
you can
fine.
actually see the generation,
Good trajectory.
the altitude there.
She's climbing straight. On switch is safe. We have a booster burnout.
Okay, this is some results from Dr. Wan's lab. They do combustion, and you can see the movement of, I guess I should have started this one. They actually study the combustion of moving air. It's the same principle, but their velocities are so low that really doesn't really generate any thrust, right? You can see the combustion here on different measuring techniques or visualization techniques, as you can see. And yeah, there's nothing. Dr. One is the only, if you are interested in propulsion research, he is the closest person. He doesn't really do propulsion though, so keep that in mind. And a very interesting, I guess, thought about the CO2 emissions. That the cradle-to-grave CO2 emissions for all of these propulsion methods, electric, hybrid, and also internal combustion engines, are very close to each other. So electric vehicles, at least at this point in their life, don't really save the environment. But that's no, they're pretty cool cars. Have you ever driven a Tesla?
They are cool.
They are very smooth. Yeah, they are very smooth. They are very cool. I actually, I had an electric vehicle. I had a BMW i3. It was a very cheap car. I mean, you could buy the used one for a very cheap price. But I ended up selling it because of the range. Yeah. 70 mileage, yeah. But that's, it is a good car though. I love the car.
What was it?
BMW i3. I mean, if you are thinking of buying it, you should definitely buy the used. That's, they are not that expensive, believe me. It's like cheaper than a Toyota Corolla, used. Yeah. Okay, so let's actually let's stop the lecture here. And I know all of us wanna get out of here as soon as possible. So let's stop the lecture here. And then next lecture, what we are going to do is we are going to go over the mathematics of it, just a little bit though. As we just want to cover the homeworks, right? Then we are going to come back to the Brighton cycle later in full force, and we'll spend like a month on Brighton cycle, right? And that's going to be Monday, right? And on Wednesday we are going to, if we are fast enough, we are going to start going to the propulsion book. Have you seen the propulsion, Dr. Farrow's propulsion book? No. So we have two textbooks for this. You didn't know that? We have two textbooks for this course. One is the thermodynamics by Moran and Shapiro. The other one is propulsion by a guy named Farrow from Kentucky State University. Make sure you at least have a PDF of that. That book is going to be very important, right?
We need to bring the book with us.
If you like to, yes, but I don't see how that would help. There are a lot of equations though. Make sure there are millions of equations, right? And I will upload the PowerPoints, but I will never use them because then I will just go forward with the PowerPoints and you won't have the time to write down the most important point. That's why I'm going to write them on my tablet. Any questions? Yes.
Whenever the senior class of aero graduates, is where we get employed and how soon we get employed when we track at university? Because I know we're still in the process of getting accredited.
Yeah. The accreditation part doesn't really have anything to do with your employment, so you shouldn't really worry about that one, right?
Well,
Yeah, and I understand if you are worried, but that doesn't really affect your employment whatsoever. Okay, that you shouldn't really worry about. But where you are going to graduate, how soon? I really it depends on you, right? I don't know how to answer, but whoever in our graduating class, whomever has applied for the jobs, I don't know the correct grammar here, but could get a job pretty soon, right? I guess there were only 2 people who really applied for jobs. Two other didn't graduate, and one of them went to MBA. One of them is doing her master's. Yeah. I guess Tyla is also doing graduate work, right? Tyla, you don't know her, probably.
I think she did.
She found a job. She found a job.
I think she mentioned somewhere down in Florida.
Okay, so like 2 of them. What's that? She's still here? I haven't seen her. I only know about Ryan. They didn't really fill out their exit surveys, despite my numerous emails. Probably for the design course, I'm going to